Hi everyone, how's it going?
Good morning, everyone. Welcome back.
Yeah, so if you are new here, I'm Felipe Matias. I'm talking from North Dakota State University.
And I'm Claire Gahagan. I'm here from Agriculture Canada.
Perfect. And this video today, we just want to start saying thank you for everyone that came to talk with us during the conference last week. Actually, this week was the society meetings in Salt Lake City, and then was awesome receiving feedbacks. So thank you again for watching our videos. Uh, it's great to know that when you have that feeling that you're doing something, something that is helping. So continue sending your feedback, and also if you have your pipeline and want to share with us, just contact us and we can organize a workshop for you. Okay, any feedback is very important. And today we have here a member from Drone to Phenome, because this workshop series is a partnership with Drone to Phenome group, and I want to invite David.
Hello. Yeah, thanks, Felipe. Yeah, so we're from Drone to Phenome, coordinating with the PhenomeForce for this series that is talking about methods to share data, pipelines, and protocols. So the Drone to Phenome effort is meant to bring together people who are interested in learning how and developing these methods and making them available to the rest of the community.
Awesome.
So in addition to that, we're about to launch a survey, an international survey of barriers to entry for UAV owners. So thank you.
Yeah, great. So yeah, our series is called Principal Protocols and Pipelines for Drone Phenotyping. And we always do this introduction, right, Claire?
Every week.
Every week.
So we're PhenomeForce, and we're a community looking to connect and empower people working in phenomics by building an online library of resources and trainings. And if you're watching this video, you've probably found our YouTube channel. You can look back in our history. We've had plenty of very interesting speakers on different subjects in phenomics. And if ever you're interested in suggesting a topic for a workshop or you have questions, you can reach out to us at our email. We also have a Slack community you're welcome to join. And to join that, you just need to send us an email as well.
Awesome. Thank you. Yeah, this is the Drone to Phenome. David already did the introduction, talk about the project. But here we are in partnership with other colleagues from different institutions, and we are just starting. And if you want to join us, please send a message. Right, David? David is here to help us to answer questions, and feel free for suggestions too. All right. And today, I'm very happy to have Zhou Zhang here, because we have an overlap of a year at UW Madison, and we had the chance to have some meetings together, and she's great. So, hi, Zhou.
Hi. Hello, everyone.
Yeah, it's awesome having you here. Today, she's going to talk about Alfalfa yield and quality predictions using UAV based in hyperspectral images. Hyperspectral images. Thank you for coming.
Okay, it's my turn now?
Yeah, go ahead.
Okay.
Go ahead. So if you have questions, you can type your questions here in the comments, and then Claire, David, and I we're gonna talk and pass the questions for Zhou Zhang. And feel free to, yeah. And anything else, Claire? Okay, okay. So it's all yours.
Okay, thank you. I'm so happy to have a chance to talk here. Maybe I can introduce myself first. Right now, I'm an assistant professor at University of Wisconsin-Madison. I joined the UW Madison in 2019, so it's been about 2 years. And here I'm in the biological system engineering. Actually, it's also agriculture biological system engineering. We does a lot of agriculture engineering things. And here's my website. In our digital Ag Research Lab. Here, our research mainly focuses on combining the remote sensing and machine learning tools for digital agriculture. It can be like high throughput plant phenotyping is definitely a main focus. Also, we work a lot on the precision agriculture applications, like for water management, nitrogen management, disease detection. Also, that's for one side of my work focuses on these fine scale studies, which we use these UAV tools for data collection with different types of sensors. Also, my another side of research focuses on large scale agriculture crop monitoring, like in like crop growth monitoring and yield prediction using the satellite imagery and machine learning. So in this case, we are talking about for the state level or even the entire for the whole country, national level. So this is mostly for large scale studies. I also want to mention that if you are interested in either the satellite remote sensing or the drone remote sensing and interested in data, machine learning, feel free to contact me. We are actively recruiting for PhD students starting from 2020, as well as postdoc scholars, which does not have any deadline. You can apply anytime. And yeah, we are looking for one postdoc and multiple PhD students joining us. Also, a good thing is like our department doesn't require GRE, so don't worry about it. That's for my research intro. Also, next thing before I go to the slides, I wanted to introduce this Twitter. This is
you can press the hide in this bar below there in the presentation screen. You see on the bottom part? Just press hide.
Bottom part.
Yeah, where?
Oh, I see it.
Here we go. Perfect. Thank you.
Great. Thank you.
Thank you.
So this is my Twitter account. Just you can find me and add me. And I want to share some drone data collection pictures. So today I'm going to talk about alfalfa yield and quality prediction. Today's case study mainly focus on the precision ag, how to do the machinery, traffic management for alfalfa harvesting. But we are currently still collaborating with Minnesota, University of Minnesota and USDA ARS there. They have alfalfa breeding trials. So a couple of weeks ago, we drove there and used our drone system collect over their alfalfa breeding trials for winter survival purposes. This is picture and for alfalfa, why I focus on this because it's a main crop in Wisconsin. And in Wisconsin, we have a big dairy industry. So alfalfa is one important feedstock for dairy cows. And another one is corn silage. I also work on corn silage using the hyperspectral imagery. And here is a picture. We used our drone system to monitor the pasture as well as the cows' behaviors. Then we want to connect the crop data as well as the animal data, combine both input data to predict the milk production. Yeah, this is the cows are near to the electric fence, and we want to collect RGB imagery over them. So this is interesting. Yeah. Also, this is our drone system. This is what it looks like in the sky. Yeah, I want to talk about this. So our drone system, right now we have 3 sensors mounted on this drone system. One is the hyperspectral camera, which I'm not going to talk about today. So it's in this black box inside it to protect it. And this one is a high resolution Canon RGB camera. it can give us the high spatial resolution RGB data, so we can monitor the animal behaviors. And also, this is a LiDAR sensor. So we can, LiDAR, we can capture the 3D structure, extract the plant heights. Yeah, so all these three sensors can kind of complementary each other. So we integrated them together, one drone system, so we can obtain this multimodal data. Also, we have one APX, Trimble APX integrated also within this hyperspectral system, with the hyperspectral camera inside this black box. This was a relatively high performing GPS IMU system, because we all know that for UAV, we need to deal with the geometric correction, especially for this push broom hyperspectral camera. We need to align for each line, right? At each time, we only collect a line data, not a frame data. So the geometric correction has become a bottleneck for people working in this area. So by using a more high performing GPS as system that can give us like a centimeter resolution, so we don't really need to manually extract data, because we have a good GPS data to also rectify and mosaic the image. Okay, that's what. Then now I can move to the slide start about today's presentation. Okay. So today I'm going to talk about this alfalfa yield prediction, yield and quality prediction using UAV-based hyperspectral imagery. And here is our digital ag website. You can visit this website as well as my Twitter account to learn more about our research work. So my research, I graduated from Purdue University in the civil engineering, and my research there were focused more on remote sensing side. And then after the PhD, I went to University of California, Davis, and I work on remote sensing for almond yield prediction. So my research, one side of my research, like using these different remote sensing platforms, is can be satellite imagery, can be drone imagery, or even some ground robotics, and then develop machine learning models to extract the informative features from the multi-modal data, and then to support digital agriculture applications, like can including both precision ag and plant breeding, phenotyping. I guess most of you know hyperspectral data already, but just in case, so here, talk a little bit about hyperspectral data. So we know that multispectral, usually we have like 5 to 10 spectral bands, and the hyperspectral have much more than that, usually more than 100, 200 spectral bands. Each band is about less than 5 nanometer spectral resolution. So instead of seeing this discrete individual values for each pixel, for hyperspectral, we can see a continuous spectrum, which gives us more fruitful spectral information, from which we can learn better about the object's properties. And it has a wide range of application, right? And the precision ag, and it's a big application area. Other than that, we can also apply this, for example, like food quality detection. Since I'm in the ABE department, actually, lots of people in our department focus on the food engineering side. And hyperspectral, if we put a hyperspectral image indoor, we can use that to detect the food quality as well. So alfalfa is a valuable forage crop, and it's an important feedstock for the dairy cows. And it has a high yield and good nutritive values. Unlike other, alfalfa is a perennial crop. It usually can last for more than 3 or 4 years. And unlike corn, soybean, or other common crops which we harvest them only one time in a season. Alfalfa are harvested multiple times in the growing season. Different places have different harvesting schedules. Like here is different with California. But in Wisconsin, we usually harvest them 4 to 5 times in the summer, and it follows a monthly harvest schedule. More precisely, people use the 28 days as a guideline for the harvest. So the first harvest typically happens in June, and then July, August, September. Then we will allow the alfalfa to grow through the winter time until the next season, May. Then we will harvest again in June. So in the alfalfa harvesting, it involves lots of this machinery traffic. So maybe this picture can give you a better idea. First of all, we need to use the mower to mow the cut the grass, the alfalfa. Then we need to leave them in the field. Then use another machine to rake it. So we can have the upside down. We can let the alfalfa to completely dry. Once it's dry to a certain degree, we will bale it, something like this. Then we can transport it to store it. So each type of operation requires a different set of machinery. So you can imagine this alfalfa field will be have multiple machines applied in each harvest, right? Every month. So this will cause a problem for both the crop as well as the soil health. It probably will affect the soil compaction. Then people wanted to evaluate how to really minimize the traffic and how this traffic really affects the alfalfa crop and the soil quality. Traditionally, like phenotyping, we just go to the field, do the destructive sampling, and collect the alfalfa samples from different treatments. Then we compare their yield, then we compare their quality, and see how these different treatments affect them. Nowadays, we think whether maybe we can try, right, using this drone technique with hyperspectral imaging to estimate this alfalfa yield and quality. This research is, although the tools are not novel, people use this kind of hyperspectral tool for different crops from recent years already, but applying it to this forage crop, especially alfalfa, is kind of relatively new. Still very few people work on this type of forage crop. This is the old system we used before the upgrading. So in this system, we still use the gimbal to stabilize the camera, because on this is 2019, we just came. Our lab has only a hyperspectral camera. Also, this GNSS INS system is the standard performance, not the high performance. And the geometry collected by this system were not really well aligned for the imagery. So we have to manually correct those errors. So after that, I decided just to upgrade the system by adding more sensors, and also upgrade this GNSS INS system to a more high-performing one. So we don't really to worry about the geometry errors. And then we did our research studies at Arlington Agricultural Research Station.
Zhou, could we? Sorry, there was just a question about your GPSs, and I was wondering if we could just ask before we move on. So they were just wondering if your GPS requires a ground station, and if you could just name the model that you use for your GPS, if you know it offhand.
I don't need a GPS ground station. For the one we just upgraded, it's a Trimble APX. You can still put a GPS base station, but that one also has another function called a smart base, which means they can use the I believe every state has some GPS networks. So you can use the nearby established GPS networks to do the differential GPS to provide you a much higher resolution. So to save time, we usually don't deploy the ground-based GPS.
Perfect, thank you.
Okay. So this is our experimental side, and so each black box represents one plot. This is different with breeding trials because our plot is much larger than the breeding plot. Each plot is about 3 meter by 3 meter, and this is mainly for precision ag applications. And we randomly applied 7 different levels of machinery traffic treatments, and with 3 replications for each. So here is the list of the treatment we applied, and we try to simulate a different traffic application. As you see earlier, we need to first moor it, then rake it, merge the alfalfa, then bale it, then transport. So different treatment means we apply different number of passes of the traffic on the crop, so they can simulate the different traffic effects. For example, T1 has only 1 pass. We only simulate the mower traffic. And then T7 is a control group, has 0 passes applied. And then T6 have like 5 passes, then it can simulate a series of all the traffic applied on the alfalfa plots. Yeah, this is our platform. I want to mention a little bit more about this hyperspectral camera in case you are interested. Right now, there are different hyperspectral vendors on the market, and we chose this Headwall Nano, and this is also a reason is that it's relatively small, as you see here, right? It's just about like this size, and the weight is very light. So the UAV, the payload is an issue, and it has internal storage, so it's very convenient to use. And the spectral resolution is good. It's covered the visible near infrared range, 400 to 1000 nanometer, and with this number of spectral bands. And spectral resolution is 2.2 nanometer. And it's a line camera, it's a push-pull camera. So each line contains 640 pixels. Say if we fly 440 meters above the ground, so the image width we can scan on the ground is about 30 meters. Yeah, we did a few flights in 2019 and a few flights more in 2020. This is our typical flight parameters, like 40 meters above and 5 meters per second. And then the spatial resolution, or the GSD, is pretty good, less than 3 centimeter. Even for the breeding purpose, when your plot are much smaller, this is enough, because we use this system also for the corn silage breeding trials. And this is how we set up our hyperspectral. This is just alfalfa, as you see. This is alfalfa plots. And yeah, we put this in a big case. And this drone requires like 6 batteries just to use it. And then we upload all the parameters into the camera using this cable, like polygon, like flighting parameters. After that, we can just unplug the cable and then let the drone to take off. This is the old GPS. So these 3 antenna are for the drone. These 2 antenna are for the onboard GPS. Hyperspectral, we need to do the radiometric correction. First of all, we need to convert the digital number to the radians. The vendor usually supply these parameters. We can do this easily. And then another step is to convert the radians to reflectance. We deploy these calibration panels close to the field that you are flying over. At a minimum, we will need 2 calibration panels, because we will fit empirical line model, just a linear regression model. You need at least 2 ground truth point to get a parameter for the linear regression. But the more the better. Usually we use 3, and they have different reflectivity. One important thing is when you deploy such panel, you need to make them really flat. When we purchase this whole package from the Headwall, what they give you is not something like this. They give you a super big panel with all these 3 panels connected together. Then it's like a 3 meter by 3 meter tarps. And it's very inconvenient to use it in the field because it's big and it's difficult to make it flat. So I just cut them into 1 meter by 1 meter pieces. So I will have 3 sets of it, right? I will have 3 sets of it. Each time I use 1 set. If it's become dirty or something, I change to another set. I just mount them on a board to make it flat. And then the hyperspectral camera, we don't really need to oh, okay.
Can I make a question here?
Sure.
So just repeat again about the equations to transform digital numbers to radians is provided by the person that developed the sensor, right?
By the vendor, yes.
Okay, yeah, that's a question that I always receive, and just to let clear, for people that is watching today, that these first parts of transformation from digital numbers to radians are equations provided by the vendor, right? The person that is selling the sensor. And the second part, radians to reflectance, you need to do during your flights.
Yes.
Perfect. Okay.
The Headwall software can do all this together, but I just feel like they're I'm not sure if I can say this. I just feel like it's not very easy to use. So I just write my own code. For the first step, I use their software. For the second step, I wrote my own code because their software will only allow you to choose 1 panel. They will not allow you to choose 3 panels to do the correction. Using only 1 reflectivity is you have only 1 point. So the conversion wouldn't be very accurate. So I prefer to use all the 3 colors I have. So I wrote my own Python code.
Okay, great. If someone contacts you, you are able to share the code for
definitely.
Perfect. Yeah, thank you.
Also, one thing, since you talk about DN to radiance, I probably can add that. The hyperspectral lens is very expensive. Not only because of the hardware, but also because of the calibration. So if you accidentally drop it, even it's not really physically damaged, you still have to send the sensor back, the lens back, the whole thing back to the vendor. They will need to recalibrate to you, depending on how you negotiate with them. If it's outside the warranty year, usually you have to pay a few $1,000s just for the calibration. And then they will send you new parameters for converting DN to radians. So be careful about your lens.
Yeah, perfect. There is go ahead, Claire. No, go ahead.
I was just making sure we got to the question. I think that there's still a little bit of confusion about the tarps and the correction you're doing with the tarps. So I just want to have a bit more detail on how you use at least the 2 tarps for the regression and what you're actually doing with that regression in terms of correction.
Sure. So, okay, you deploy this close to your field, right? Your drone will fly over these panels. So your sensor will measure the reflectance values for all these panels. That's your measured value. That's not something correct. That's something that's the measured value. You want to correct those values. Also, you actually know the spectral reflectance of these panels because these panels are not random fabrics. They are very well calibrated, so they are not cheap things. Their reflectance values do not change across the days. Say if today is sunny or tomorrow is cloudy, they don't change. They are consistent. So you can think of them as ground truths. Now you have your ground truths, you have your measured values. You can develop, and usually we think their relationship like a linear. So we just build a model like ax plus b equals to y, which is a linear regression model, right? Your x is your measured value by the sensor. Your y is your ground truth value. Then you can try to learn the parameter a and b. To solve this equation, you at least need two things, right? But usually, if we do the least square optimization, then the more, the better. That's how it works.
Okay, so I guess their concern was just that they only had one calibration panel. So you're saying to do it properly, they should have a few different.
Yeah, for one, they just assume the linear regression is y equal to ax without b.
Okay, I mean, that's good. Thank you.
Okay. So then the next step is geometry correction. This is this is a little bit different, also different with the multispectral or RGB. For those, we usually what we do, we deploy the ground control targets, right? And then we use them to correct the geometry. But for hyperspectral, we usually don't do that, because even we do that, it's useless. If we deploy, we need to deploy lots. It's a line camera. So we completely relying on the onboard GPS and IMU system to correct the geometry. So the more accurate your GPS IMU system, the more accurate your geometry for the image. And also, similar to RGB and multispectral data, we need to have a certain amount of overlapping between flight passes. For this, usually we can set them like 30%, which is enough to avoid any data gaps. So this is, we just run their also rectification software. So you can see some overlapping between these passes, and then we do the mosaic. This is all provided by the vendor. You can just click the software. They just do it. Yeah, that's for the pre-processing. Any questions so far? If no, I can move on.
No, you're good to continue.
Okay, thank you. And then what we do is, yeah, we extract the. We also need a plot polygon, right? So we know the plot. We have the shape files for the plot. Then we can extract the plot level data. We use the mean level. Within each plot, we have hundreds of pixels. We extract the mean value. Yes, you can also add a standard deviation, but in these studies, we only use the mean. And then we draw this hyperspectral reflectance curve. We compare the spectral curves between treatments. So T1 is one pass, T7 is the control group, which is 0 pass. So you see here, T1, T7, the two spectral reflectance are just overlapping each other. We don't have seen much difference, which is reasonable because we have only one traffic applied. It may not really that obvious from the reflectance data. But if you look at this one, it's the comparison between the T7 and T6. T7 is the control group, which is the blue line. T6 is the 5 passes traffic, which has the most severe traffic treatment applied, is the T6. So you see a significant decrease of the near infrared reflectance, right? This makes sense because we know that when the plants are kind of under stressed, we have a lower NDVI value, which means the NIR decrease and the red band increase, right? We also see a small red band increase here. So it means the hyperspectral data can help us detect the differences between the different machinery treatments. By seeing this variability across the plots, it provides us a good foundation for us for the modeling purpose. Because if we don't see any difference across these plots, we cannot develop a reliable model because there's just everything is the same. Then regard modeling, we can use the original 270 bands, or we can just extract some vegetation indices from all these original bands. In this work, we explored all the existing literature about hyperspectral imaging. We extract the 80 published hyperspectral indices. All these indices are narrow band indices. For example, here, within all this category, they are all called NDVI. But because of this narrow band, there are different versions of NDVI. They use different bands for the calculation, so they have different versions of NDVI. Also for SRI, right? So we put them all together and use this 80 vegetation indices for our yield modeling. They use as input variables for our yield modeling. Then further, we applied a feature selection method to further reduce the data dimensionality. We apply a recursive feature selection approach. Also, this is a relatively well-used feature selection method. It includes 3 steps. First of all, we run an estimator it can be a regression model to determine the initial feature importance. Then we remove the feature with the lowest importance score based on this first step, right? The first step gives you a feature, just rank all the features, and then you remove the lowest one, and then you assign the ranking to the removed variable according to its removing order. Then we just do this recursively. For example, we have 80 bands, then we do this 80 times. Until the 80 times, we have only one band left. That one is the most important one, right? Because it's the last one to be removed. Yes, we know the random seed, because we do machine learning, right? You give a random seed, how to separate the training and testing, it gives you a different accuracy or different results. Then to be more reliable, we just do this 250 times. Then we see some vegetation indices are consistently ranking higher for this dark red. Then some others, like in this part, this is the ranking, right? Then we try to find the ones that are consistently ranked higher than others. Then we use that for our machine learning model development. Regarding the model, here we develop an ensemble model. We know, like machine learning model, we can it's usually it's individual model. We train the model and then we apply it. For example, the random forest, people use this widely, or deep neural network. It's just a one model. For the ensemble, what we try to do is we combine the multiple model prediction results together, and then we assign different weights to different model. We do this weighted aggregation, right? And then the important thing is then becomes, how can we construct this ensemble model? There are some things to be considered here. First of all the base model within this ensemble needs to be accurate enough. We call that sufficiency. It needs to have high sufficiency, because we don't want a model that performs very badly, and then it will affect the ensemble final outputs. Also, we want the models, base models, to be as different as possible, because we want to have diversity and reduce the redundancy. For example, if we use 3 random forests with each model has a different number of trees, it can be it can still be 3 models, right? For each model, it have 10 trees. For another model, it has 100 trees. It can still give you 3 results. But in that case, all these models are much similar. It's redundant with each other. So in constructing these, finding the base models, we intentionally try to find the models that are mathematically different with each other. Yes, you can use deep learning, but in this case, we have limited number of ground truths, so we tend to use some simple or traditional machine learning model. We found 3 models here. One is random forest, one is support vector regression, one is k-nearest neighbor. They mathematically are different with each other. So we think they are different. Then we apply this model, first of all, this 3 model individually to see how well it performs. R square is the accuracy, right? Closer to 1 means higher accuracy, closer to 0 means lower accuracy. For each time, we only add in, we have the feature ranking already based on the feature selection method. Then at each time, we only add in 1 feature. We want to find out how many features we want to use. We don't want to use all the vegetation indices. We want to reduce the data dimensionality. Then we find out that after adding 25, as you see here, all the 3 models tend to converge. The accuracy are stabilized. They don't really change much after this number. So we set 25 as the cutoff point. Then we only select the top 25 features for the model development. Then this is the scatter plots, the prediction accuracy. So A, B, and C means the 3 individual model, random forest, support vector regression, and the k nearest neighbor. And D, this one is the ensemble model, which combines the prediction results of all the 3 models. We found out that this one gives us the highest performance. Also, as you see here, we can clearly see 2 clusters, one in orange and one in green. This is because we use the 2 harvest ground truth data for the model development. So one cluster is the yield harvested from July. One is the yield harvested from August. So we can see the alfalfa yield are different at different harvesting time. Usually the later harvest tends to have a lower yield. Maybe because we have so many cuts beforehand, the alfalfa do not really have enough time to regrow, so the yield can be reduced. The June harvest typically has the most highest yield because it has the whole winter to let the crop to grow. And then we applied our model back to each treatment. We found out the ensemble model performed consistently well, better than the others for each treatment. This further validates that the ensemble model is useful, and then it's better than using the individual model. But the only thing you need to pay attention is the sufficiency and the diversity. Okay, when we're developing the ensemble model. That's for the yield prediction part. And then now I want to continue and talk about the alfalfa quality prediction, which is a little different with the yield. When we talk about the quality, actually the quality matters even more than yield for growers for alfalfa, because the quality, like these nutritive values, crude protein, acid detergent fiber, neutral detergent fiber, all these quality directly affect the alfalfa market price. Traditionally, there are 2 types of methods to determine these quality values. One is the chemical methods. You just sample it and then go to the wet lab, run the chemical machines, then you get all these values for this CP, ADF, NDF. This is so slow. And then later, since 1970s, actually more than 20 decades ago, people started using this NRS, which is near infrared reflectance spectroscopy. It looks like this. Then you have your sample, and then you put your sample here, then let it scan. It also gives you like a hyperspectral reflectance spectrum. Then they have the already developed calibration equations, so they can use that to directly give you this nutritive values. This has been used as an alternative approach in the compared to the chemical analysis, and the accuracy can be like 99%, something like that. Even though this got improved compared to the chemical method, this is still slow, right? You can think you need to go to the field, do the destructive sampling, sample it. After sample it, we need to wait the alpha to dry. After dry it, we need to grind it into small particles. And then we need to scan each sample. Usually for each plot, we grab more than one sample and then calculate the mean to represent the plot quality. So this is a lot of work. And this is kind of expensive. To run this one sample, it almost just cost $20. We can imagine for the breeding trials, if we do this for the thousands of plots in the field, it's a lot of money. Then, since the NIRs use hyperspectral reflectancy, is the idea is the same, then we just think whether we can just have the drone with a hyperspectral camera mount on it and then fly over the field, then develop a model to estimate quality. Then we did, I would say this is the first study. I searched the literature, I didn't really see anybody does this. So we just, the first group to do this type of work, estimate the alfalfa nutritive values or the quality using this UAV-based hyperspectral images. So as you see earlier, right, this is not a single value, not like yield, you have only one output. This has multiple outputs. Then we thought whether we can develop a model, just this model can predict all of them together rather than develop a model for each individual trait. Because one side is easier to just predict all of them together. On the other hand, because all these nutritive values has some underlying relatedness to each other, maybe we can explore the underlying relationship to further improve the prediction model accuracy. Then we borrow the idea from deep learning, this multitask learning neural network. Then we design this multitask deep learning neural network. So we have the input layers. This is the input data. In this case, we, instead of using a single time data, we collect hyperspectral multiple times. So we have time series data. So each blue block represents one time series data. Then we input them into this long short-term memory module, LSTM, which is a widely used deep learning time series module. Then we input this into LSTM. This is the common part. For any nutritive value here, we don't separate them. We put all the data together. This is called common hidden layer. And then we extract the common features that can probably be useful for all the nutritive values we want to predict. Then with these extracted features, we also further develop this task-specific layer. We call this task. For each task means each nutritive trait. So this can be CP, this can be ADF, this can be NDF. Then we can add another block even to predict the yield. Then we can predict the yield and the quality altogether. So we have the common features used here, and then we have the task-specific layer, right? Because we know using only the common features will not work. We still need to have the task-specific features. Then we further extract some task-specific features using the this individual hidden layers in each block. Then we predict for each individual yield or quality trait. And we further compared our results on all these quality variables to some other single task and other traditional machine learning methods. SVR is a regression model, random forest, and artificial neural network. STL means a single task learning, which means we still use a deep learning model, but without the multitask module. And the multitask learning is the model we develop. And the bold means the highest accuracy. We found out this consistently higher than all the others for all the three traits. And then we predict the quality for all the 3 times harvest. One harvest in July 6, one harvest in early August, and one harvest in late August, and using different color. And for the CP, we can see it's kind of easier to be predicted than the ADF and NDF. So overall, we still got pretty good R-square for all the 3 methods. But we just found out the CP is the best one because it gives us even more than higher than 0.8. Others like 0.7, 0.66, closer to 0.7. But CP is the best because they all concentrate very well on this line. And then from top to the bottom, representing for different approaches, we found the multitask learning is the best one because you see the points are more concentrated, others are more spread out. Some conclusions and thoughts for the future. We use the vegetation indices. We select the important indices. We find out that we know the vegetation indices usually involve 2 bands, sometimes involve 3 or 4 bands. We found out that some multi-band indices, like the 3 or 4 band indices, rank more importantly than the 2 bands, which means that probably more spectral information, the better. Also, like photoreflectance index, which indicating the photosynthetic efficiency, ranked importantly, consistently. Regarding the ensemble model we use for the yield prediction, we found that it achieved a better performance than the individual single models. Also the sufficiency, which means the model needs to be accurate, and diversity, which means the models in the ensemble need to be different with each other, are the 2 principles when we constructing this ensemble model. When we predict the quality, we find that the multitask learning is an important, useful tool, and it outperforms the state-of-the-art single task learning models. So in the future, we wanted to apply these tools to the alfalfa breeding trials when the plots are much smaller and more ground truth data. We want to see whether they can give us good results. My understanding is that I also work on corn, including both green corn and the silage corn. My found out is that actually alfalfa using the hyperspectral data is easier predicted than the grain yield for the corn, because alfalfa is just pure grass. You can monitor its canopy, but not like corn is you need to detect the grain yield is related to the kernel. Maybe sensing only the canopy would not be sufficient. The corn yield typically only give me like 0.5 R-square results, but for the alfalfa, we can achieve 0.8. Yeah, that's all for my presentation today, and I'm happy to answer any questions that you have.
I have a question. Show it here. I was wondering if a lot of the indices that you describe were developed for multispectral devices, satellites and such. And now that you've got so many additional bands, have you considered looking for new indices? Or like new permutations of these bands that could give you additional information?
That's a very good question, Ray. We didn't really develop our own index. We just explored the existing one. But yes, I think once we find out the most important bands, maybe we can construct the new indices using those important bands.
Okay, and we have another question. So the LSTM model is very interesting. I was also interested in that. I'm curious to learn more about this, how to incorporate time series into machine learning models. But the question from Yaping is, do you think it can be used for nitrogen content prediction in leaves?
Yeah, definitely. So it has no limitation to your application. It's just for your data, whether you have this time series data or not. By saying time series, I mean at least you have 3 temporal points.
Mm-hmm.
Yeah, perfect. I have some questions too.
Sure.
You said that the same sensor that you are using in the drone, you also using in lab to collect images, right? For example,
I haven't yet, but you
Okay.
can. But then you will need a different setup.
Okay.
Mm.
And then in this case, for example, you can evaluate disease and leaves and seeds with the same sensor.
Definitely, I see people do this.
Yeah, we were trying to do this, and the image is too big. For example, each image from a lot of seeds, it was almost a gigabyte, and then to evaluate this data was very hard. Do you have any suggestions what to do?
Is it hyperspectral image?
Yeah, hyperspectral image. Yes.
Oh.
How you feel about reducing the quality or the resolution? You agree?
Yeah, that's a good question. I didn't really reduce the data resolution. I think maybe just reduce the bands. You can, the most easiest way is you just first of all you bin the spectral bands. It give you 200 something. You just bin by 2, then you got only 100. You can do this even in the setup firmware. You automatically extract much fewer spectral bands then.
That's a good suggestion.
Then you can go even bin by 4, then you got only 40, right? Maybe as the initial study, you just try to see whether this sensor works. Then once you have an idea, you can increase more and more. That's the easiest way to reduce it doesn't require any additional programming or anything.
Okay, so in this case, you recommend, first of all, besides reducing each layer resolution, it's reduce the number of layers.
Yeah,
that's the best suggestion. Okay,
yeah.
That's a great suggestion. I have a couple other questions here. I don't know, David, Claire.
Yeah, I have to go to a meeting, but yeah, sir, I'm going to miss it. I'll catch up on YouTube.
Yeah, great. Thanks for coming.
Great. See ya.
Yeah, thanks so much, Zhao. I enjoyed your presentation. Bye.
Yeah, for example, you are right. I worked with tropical grasses before with one crop called Brachiaria. And I never found also a paper that was doing what you guys did, try to use the hyperspectral to evaluate quality. And that's something that I guess is going to help many people, and also is the future, because it's really timing, consuming, evaluate quality on forage. You know, right? Exactly. Dry, grind, and evaluating in NIR. So in this case, are you using the comparison, the ground truth? You are using the chemistry, or the chemistry results per sample, or the NIR results?
I use, because we got our ground truth from the forage lab. Right now, most forage lab just use the NIR. They trust that very well.
Okay, yeah. But you think that is better, would be a good suggestion, also compare with the chemistry, general chemistry? Or
I don't think you need, unless you have lots of budget.
Yeah, that's great.
That's also what I was suggested by some Alfalfa experts from other universities. NIR is sufficient.
Cool. Claire?
I really enjoyed your presentation. I don't have any questions right now, just because I haven't worked with hyperspectral data before. But it's cool to see you getting to actual interpretable results from such big data.
Okay, thank you.
Yeah, About the softwares, about the machine learning analysis, which software libraries you are using? Are you doing this in R, Python, or any other platform? And which libraries for implement the machine learning?
Yes. All our codes are programmed in Python. Yeah, we can share the code later after we organize it, since the paper are published already. We for the traditional machine learning, we just use the scikit-learn. I believe most of people use that. For the deep learning, we use PyTorch. So it's also an embedded library in Python.
Okay. So could you share with us later the link, and then we can post here in the
Yes, yes.
description, and then anyone watching the workshop can just follow there and also send questions to you.
Sure. No problem. Yes.
Yeah, great. So anyone over there, please type your questions in the comments. We still have some time. But let's use this with your experience. So normally your students, they go to the field, or they are more the computer guys? That's one question that we always receive. And what do you think about this?
Yeah, my student go my student do machine works, real machine works in the summer, then machine learning in the in the fall and the spring.
Great. Another question that we also receive is, in your pipeline, the stitching, which software you are using to do the orthomosaics, and which resolution is normally your, orthomosaics?
Yeah, all the mosaics is 3 to 4 centimeter. That's good for both precision egg and breeding, I think. And I think that the software depends on the vendor. You buy the sensor from which vendor, then just use that. That's what I found out. I don't really see um some common some uniform hyperspectral software. I really never see that.
Mhm.
Yeah, still.
Yeah. Okay. So I'm not seeing any questions here from people watching there. But anyway, you guys can send message later and also contact any one of us. And Zhou Zhang, I'm pretty sure that she'd be happy to to answer. She also said about the possibilities to have new students in her lab, so please contact her if you are there watching. Share this video with your colleagues. I know a huge group of people work with tropical forage in Brazil, where I
Oh,
worked before,
okay.
and they also are starting using the technology to do evaluation on livestock production,
Okay.
and one of the ideas is also evaluate how it is the impact of the animal on the on the forest, uh, the harvesting process, and then
Oh,
how the amount of animals per area can be evaluated using drones. So that's something that's coming soon too.
sure.
Here in Alfalfa, normally is only for do the hay, right? Or
Yeah.
you did evaluation with animal behavior too.
No, for Alpha, no. But I'm working on another project for pasture. For pasture, yes, that's for dairy cow. For the grazing management. That one is we will very similar techniques tools. Hyperspectral to estimate the pasture yield and quality, and RGB camera to monitor the animal behaviors, and then combine the animal and crop data, integrate them together to really estimate the animal output, like the milk production.
Perfect. Yeah. Another use on animal science there is going to be evaluate the impact of shadows in
Oh,
integration system with trees, and
oh,
that's another very amazing tool because you can using vegetation indices and apply mask, you can recognize the area where we have shadows from the trees, and then you can, get some estimations in different times in the day. And the way that you show how to do the multitask evaluation in different times for harvesting, you also can do this in different times in the day to evaluate the shadows. And then I was doing these applications in my mind, and then that's a good suggestion if you were over there and working with trees and forages to start thinking on this, and maybe just change a little bit the algorithm that Zhou Zhang present today, and I guess it's a good application.
Thank you.
Yeah. We have another question here.
Oh.
Here we go. What if you use multispectral camera to do your studies? Would you expect a much lower accuracy, or maybe that would not work at all?
Yeah, that's a very good question. We never really compared the two, but what we did is we use only a few bands in the hyperspectral. Then we find out that the accuracy are much lower than using more bands. So we assume the hyperspectral can be more beneficial. But our next study is actually to evaluate this more systematically. I just got another hyperspectral, multispectral, DJI multispectral drone. Then we will use that to fly over the same fields to see whether the accuracy are significantly different.
Yeah, that's a good point. I worked with multispectral before. Was around hyperspectral before was around 400 wavelengths, and I did some comparison doing selecting the same wavelengths from the multispectral that we have, and the result was quite the same.
Quite the same.
Yeah. But anyway, that's changed, right? Crop per crop, and then.
Oh yeah.
But okay, yeah. Thank you.
That's good. Goes out.
Yes. Everyone over there, please feel free to contact any one of us. And Zhou Zhang,
Okay.
some words, some extra words for people that are watching.
Oh, okay. Yeah, nice to see everyone here. Hope you enjoyed what I talked. So feel free to drop me an email or just connect me on Twitter if you have more questions. I'm always happy to chat more and discuss.
That's awesome. Thank you for coming,
Yeah,
and let me know when you have your pipeline, and the scripts done, and then we can share with everyone. Okay?
Yes.
Thank you.
Definitely.
Bye.
Okay. Thank you. Bye, everyone.
And before we wrap up, Felipe, do you just want to put up the slide for next week's presentation so people know what they're got in store? So we're back next week, and we have Jinha, who's going to be looking at how to share UAS data using public cloud. So that's another really interesting aspect of all of this data, is how to distribute it and manage it. So that'll be an interesting presentation back here next week at 10 a.m. Central Time.
Yes, perfect. So thank you everyone for being here, and don't forget to give our like and share this video and send suggestions, okay? Thank you.
Bye.
Bye.